Hello, my name is Anastasia Skorobogatiy
And I'm Anastasia Skorobogatiy
from Quebec, Canada, École secondaire Félix Leclerc, and we did this project under an internship in Polytechnique Montréal under Katirvel Nalapan. Today we're going to be presenting our project Mobile and Cozy, wearable platform for relief of muscular chronic pain. Pain is the leading cause of disability among adults in North America. It is responsible for a greater number of disabilities than heart disease, diabetes, and cancer combined. 1 in 5 adults in North America suffer from chronic pain, which is estimated to be around 19 million people. These people can be classified into 9 chronic pain groups using computer cluster analysis and patient body pain charts as shown in the image on screen. In fact, it is not only a specific part of the body that hurts, but rather a larger area that is affected. In particular, the shoulder and neck region are present in 7 of the 9 types of chronic pain. Our project's aim is to develop a heating technology that can ease chronic pain in those who suffer from it. So heat is beneficial for those with medical conditions by relaxing their muscles and tissues, which in turn reduces muscle pain for patients. It also causes beneficial mechanisms in our body, such as nutrient uptake, better sleep, and much more. Heat is at the origin of a phenomenon called vasodilation of blood vessels, in which the caliber of our blood vessels increase due to the relaxation of our cells, which results in an increase in blood circulation. This treatment may help people suffering from arthritis, muscle spasms, and much more. Using heat to treat chronic pain is a good alternative to pain-reducing drugs such as opioids that have caused an opioid epidemic, or the overuse of powerful non-steroidal anti-inflammatory drugs that are addictive, sometimes harmful to organs, and which should certainly be avoided. Typically, at an ambient temperature of 32 degrees Celsius, humans start to sense heat. The upper limit of homeostasis for a clothed person in a low humidity environment is 52 degrees Celsius. We also emit energy. In a resting state, a human produces approximately 100 watts of power and the neck nearly 3 watts. To feel heat, the targeted body part must be heated with more energy than it emits. We therefore decided to build a prototype with a capacity to emit up to 60 watts in order to reach a maximum temperature of approximately 50 degrees Celsius. People often use bulky and uncomfortable heat packs that need to be frequently microwaved to manage chronic pain. Athletes tend to use heated coats with weak heating elements, as well as batteries of limited energy capacity requiring strong thermal insulation, such as bulky clothing. These solutions are not effective for professionals like teachers, as the heating elements are very large and obvious, nor can they customize them to go with their style every day. In order to meet these challenges, we have developed a technological platform called Mobile and Cozy for electrothermal textiles. As an example, a discrete scarf has been created using a heating element based on all-textile conductive threads that can be seamlessly integrated into any wearable product. In other words, it could be inserted into the clothes of one's choosing. The heating element can also be hidden and worn whatever the wearer's clothing style. It will also provide 30 minutes of controlled heating and pain relief.
We will now proceed with the development. In order to build our prototype, we must first ask ourselves a few questions about the technical aspects of our heating scarf. For example, how to make a fully flexible all-textile heater. Which power source should we use? How to control the amount of heat deposited on the scarf, and so on.
First, we must choose a material that are suitable for our project. Since we need a flexible heating element, conductive threads used with a standard sewing machine were a perfect composite to use. A conductive thread is made by mixing stainless steel filaments with synthetic threads. Because of their electric resistance, these wires heat up when they conduct electric current. Felt fabric sheets with good sweat resistance and good thermal insulation properties were used for the base of the scarf. To minimize heat loss, we use conductive threads on one side of the pattern and regular thread on the other. The next step involves choosing the stitch to sew the conductive threads onto the felt. Ohm's law of electricity states that the heat emitted by a heating line on a fixed voltage is stronger when there is less electrical resistance. It is therefore necessary to determine the stitch with the smallest resistance. The machine offers a large number of stitches, and by testing each one, it was determined that the straight stitch has the smallest resistance of 0.9 ohms per centimeter. After deciding on the material we would use, we started the manufacturing process. First, the base of the scarf was made by sewing together 3 pieces of felt, as we can see on screen. Then, 60 horizontal heating lines were sewn using the conductive threads. To electrically connect each of these lines, 30 vertical lines were then sewn. This constitutes the heating element of the scarf, which will be applied to the body. Finally, we sewed 2 metal push buttons to the vertical conductive strips at each end of the scarf. Using these, the scarf can now be attached to an energy supply.
To understand how our model works, we must discuss how it will emit heat. By knowing the voltage of a battery and measuring the resistance of each wire, we can determine the current flowing through a single conductive wire given by current equals voltage divided by resistance. With this, we can then determine the heat emitted by a single wire, demonstrated by power equals voltage times current. Nonetheless, a single conductive wire does not emit enough heat to have a relieving effect on the human body. It is thus necessary to increase the number of heating lines. Therefore, by adding a second heating wire in parallel, the heat emitted will increase by 2 times. Consequently, by adding n conductive wires in parallel, the total heat emitted will increase n times. We are now going to look at the design of our prototype. First, we use conductive wires 58 centimeters long, as they are comparable to the circumference of a neck. We discovered that a single thread of 54 ohm carries 0.14 amperes using a 7.4 voltage source. This current is below the maximum current of 0.3 amperes to prevent the filament from burning out. Then we found the number of heating lines necessary to release a power of 60 watts. As a heating line produces about 1 watt of heat, we need 60 lines. Moreover, the total current flowing through the scarf is estimated at 8.4 amperes, which is less than the maximum current of 35 amperes allowed by the battery. Finally, we estimated that the operating time of our prototype is 24 minutes by dividing the battery charge capacity of 3.5 amperes hour by the net current. Now let's talk about the electronic control of the heating scarf. In our first prototype, we use a 7.4 volt LiPo battery, which is among the only compact batteries able to deliver a strong current of 5 to 10 amperes, which I use in one of my hobbies, building electric aircrafts. For a 2-cell LiPo battery, when its voltage drops below 5.2 volts, it short circuits, making it non-rechargeable. To avoid this from happening, we added a protective circuit, which includes a relay. It acts as a switch by turning off the LiPo battery when it's below 6.6 volts. Lastly, to adjust the temperature of our prototype, we use a pulse width modulator, which controls the power supply by means of an electronic switch. By switching the current on and off at very rapid intervals, it controls the net current sent, therefore the heat exerted by the scarf. Once manufactured, our prototype was tested under conditions similar to its use on a human neck. To model the neck, we used a bottle filled with water at 35 degrees Celsius, and a circumference that was similar to that of a human neck. Next, a thermometer was attached to the bottle, a heating element was wrapped around it, and a heat insulator in the form of an ordinary textile scarf was placed on top of it. We set the power supply output to the max and waited 5 minutes until the temperature stabilized for roughly 50 degrees Celsius, which is the highest temperature we can get. We noticed that before the battery fully drains, the temperature actually changes slightly. More recently, we developed a second prototype in an effort to make it more user-friendly. Using a 3D modeling tool, Tinkercad, and a basic 3D printer from MakerBot, we designed a compact case similar to the size of a large mobile phone to encapsulate all the electronics. We also developed robust connectors to electrically connect the control unit to the scarf. The second prototype has been in use for about a year now, at home, at school, and during our skating lessons. There are a couple of observable technical and aesthetic problems associated with the functioning and longevity of the scarf. The main issue was the connectors, which were frequently getting damaged. Perspiration also caused a color shift and thread issues. The plastic also melts because of the temperature exerted on the scarf, destroying the wires. Finally, we observed that the resistance went up by a factor of 3. In turn, the heating has considerably gone down.
Now for the conclusion.
To summarize, during this multidisciplinary project, we made a thermoelectric textile. We learned about the effects of heat on the human body, basic circuits, advanced materials, and the manufacturing process of electronic textiles. In March 2022, our project was accepted into the Lab to Market Entrepreneurship program run by Ryerson University to explore the commercialization of our idea. The next step is to make it available to the public. Thank you.